I'm really glad to see you all here. It's getting the most from your SAN. Well, it says SAN, but it also applies to regular disk, but it's file and file group design patterns. I know it's not a very exciting title, but hopefully you'll take away something from today. So a little bit about me. I freshly minted Microsoft Certified Master, and got it last week, which is great timing. Been working with SQL Server for a little bit over 6 years. I cut my teeth as a production DBA in a 24/7 high volume operation doing financial transactions. And currently I'm SQL Server consultant with ProData in Ireland. Specialize in performance tuning and consolidation, but manage all aspects of the database engine. And I blog over there. I have two blogs. One is an old one for reluctant DBAs. One is the ProData blog. You can always get me on Twitter, @Archbold, or please feel free to get me on LinkedIn. I'm always happy to hear from anybody. So before I jump into the agenda, just to give you a little bit of background on how this topic came about, because file and file group management has always been, at least in my opinion, a management technique. So it's for sliding windows, it's for doing backups on VLDBs and stuff like that. But I came across a performance problem that I couldn't fix with a query tuning, couldn't fix with indexes, and had to approach it at a slightly different angle. And that's where this all came about. So we're going to start off with just some file group and file fundamentals, and it's just data files, so we're not covering tempdb or log files today. I'm going to look at three very common storage design patterns. So cover OLTP, data warehousing and fast track methodology, and data warehousing on a SAN. We're going to look at any other go faster buttons that we might have. And then I'm going to go through a case study. So the first half is a little bit of theory, and the second half is actually applying some of that theory to the case study that brought this whole thing about. And then when I've convinced you that this is all a really great idea and you want to go away and try it, I'm going to show you how you make the changes. And then you can call me on Wednesday, blame your boss when it all goes wrong. Right, so some file group fundamentals. So it's a general recommended practice, particularly if you're looking at large databases, so data warehouses, that you might have a separate file group for, let's say you'd have nothing but the system tables in the primary, because that way you can do piecemeal restores and get your database up very quickly. You might separate it out for differing I/O patterns. So again, if you have a fact table and some dimensions, or you have an OLTP partition, or whatever it may be, you might give it a separate little piece of real estate on your SAN or in your storage. You'd have a separate one for volatility, so say a staging area. You might not want to store that with all your main data because you don't care if that gets recovered quickly or not. And then data age is a common one as well. So again, if you manage large quantities or volumes of data, your archive data may sit out in read-only file groups on its own, gets backed up once a month or whatever. So they're just common recommended practices around file groups, and they're all around management and maintenance. If you're using multiple files in a file group, the files must be equally sized, they must be equally full, and SQL does not redistribute data automatically when you add a new file into a file group. So that's very important if you want to take away some of this stuff and start applying it in your own environment. There's a little bit of planning involved to get the data actually spread across the files. The reason you want to do that is that there's a round-robin algorithm. So if you, let's say, have a very, very high OLTP, or a high volume OLTP, and you want to load balance across 2 files or 3 files or 4 files, however many, on different disks or different spindles, if they're not all equally sized and equally full, you're going to get hotspots. So that's just something to remember for when you go and try this yourselves. I'll remind you again later. Right, the first pattern, OLTP, so online transactional processing, just in case anyone's not familiar with the acronyms. Transactional processing, it's all about speed. So it becomes less about how much data you can get on and off disk at any one time, about how quickly you can get your data on and off disk. So you want to get a transaction recorded and a user out as quickly as possible. So take, say, Amazon as an example. If you click buy now, you don't want to sit there for 15 seconds while a couple of things happen behind the scenes. You're going to get impatient after about 2 or 3 and start hitting back and stop and whatever else. So you need to make sure that you can get that transaction processed and the acknowledgement back to the client as quickly as possible. So your metric for throughput is less about your megabytes per second and more about transactions and IOs per second. And some new challenges have come along. So it used to be a case that the disk was so slow, well, it didn't really matter. And you'd have a small OLTP database, it'd sit in memory, and it'd trundle away. But transaction volumes are getting higher. Solid-state disk has completely changed the game when it comes to I/O. So because they're becoming a lot more commonplace and the they thrive on random I/O. Now you can start like really using the disk to your advantage. But as the databases can be small, file and file group layout can suffer from neglect. So an example had a 2 gigabyte database. It all lived in memory. So they were like, well, what's the point? It's in memory. It can't go any faster. Yet, when we made some changes, we got an extra 50,000 transactions per second. So we'll have a look at how in a second. But you can neglect if it's small, it's living in memory. Does it really need attention? Well, the answer is yes. Otherwise, I wouldn't be standing here telling you about it. But the faster disk does bring different challenges, because now the disk isn't your bottleneck anymore. And you want to make the disk your bottleneck anymore. Or again, because if your memory is your bottleneck, you've got other problems. So take a quick look at the pattern. This probably looks pretty familiar to everybody. You've a primary MDF file and everything lives in there. So if you'd go from a neatness and a management point of view, you might stick your reference data out into a separate file group, so your customers or your clients or whatever it may be. You may not have a volatile area, not super common in OLTP, but so I put it in there anyway. But then you might have a separate one for your transactions. So particularly if you think about some of the newer SANs that are coming out now that have the tiered storage, and they're all very clever, and they'll move your hotspots up. They'll move the data files that are seeing the most I/O, they'll put them on the expensive top tier of SSDs. So it's quite common now that you know your transactions are always going to be the hardest hit, so you keep it separate. And that way you only have to take that amount of space on your SSD tier that the transactions table takes up. You don't have to worry about references or any archive data or anything like that. So as part of the test, as I said, I took these onto a Fusion I/O card, or who's the sponsor? Violin? Yeah, it was a Violin card, definitely. And started testing. What differences did we see? So I set it up like this, exactly as it is there. And I started pumping some transactions through. And Paul Randall, and I have a link to it at the end of the deck, has a test harness that basically pumps through 2.5 million transactions just one after the other. And you can spin up as many threads as you want. So I went to 32 because it was the number of cores in the box. And I started to get this, like page latch. Like, okay, fair enough. I said, I'll keep going with my tests and added in a second file. Page latch disappeared. It's like, okay, and along with that, I started getting more transactions per second. So I started to have a look into it and look at the weight stats for each of the tests. And that's all pretty normal. Scheduler yield is something comes in, does some work in the CPU, and then says, okay, you can have it back. That's fine, I don't worry about those. But it's this last one here, this page latch up. So if we add the second file, the only difference is that's gone. So I went digging, and Paul Randall actually had the same problem. It turned out that it was an allocation page, a PFS page, in the file. What that does is every time something comes in and requests a new page or a new allocation unit, it has to hit each of the allocation bitmaps and see where it can put its page, where it can take one from, is there free space on an existing page. And because the disk was now serving all these pages back so fast, the in-memory structure couldn't keep up. So if you add in a second file, the thing to remember is that each file has its own allocation units. So you start to load balance on your in-memory units as well by adding in more files into this file group. And the difference it made with throughput, so this is completion time, 156 seconds, and I think there was 40 million transactions in total processed. Well, I was pretty pleased with that. 156 seconds, but when we removed that allocation hotspot, we knocked 15 seconds off our batch time. But you do get a lot of diminishing returns. So adding 4 files, knock 2 seconds off. 8, a further 7. So there is a sweet spot where management becomes more of a pain than the performance benefits that you're going to get back. But I'll put this in a slightly different set of numbers. If we take transactions per second, by adding in one more file, we got 30,000 transactions extra per second going through the system. And for me, for a single file, that is a massive, massive gain, particularly if you take that over the lifetime of an hour or a day of transactions. That is a massive amount of scale, just by adding in a second file. So the bit that really bugged me about this is after I made this massive discovery, and I was like, yeah, this is excellent. Anyone who's ever done any temp DB tuning, what's the first thing you do? You add in more files, because it has memory allocation problems, or sorry, allocation page problems. So it's exactly the same thing. When you, after this, go read a TempDB tuning white paper. If you've got your user databases on similar very fast storage, treat them exactly the same way. Give them the extra files. Turn on the trace flags, which we'll have a look at later. And again, just keep them equally sized, equally full. Follow all of those best practices. And you start to get throughput improvements like that. So that's the first the first key takeaway, is that your in-memory contention is actually within the file layout. It has nothing to do with faster memory, more memory. You're always going to have that bottleneck. And like I said, it's actually nothing new. TempDB has been tuned this way for years. So I don't know why I thought it was a great revelation, but I was really proud for about an hour until I figured out that, yeah, some guy in 2003 wrote this white paper. Oh well, anyway. But the thing to keep in mind is that when you do this on your user databases, it's kind of harder because you have more control over it, but it also makes it slightly harder that you need to keep your files equally full and equally sized. So just keep in mind that they're written to in a round-robin fashion, and if you don't meet those criteria at the start, then you start to get hotspots. Before I move on to data warehousing, any questions? If you do, you can just read a TempDB white paper. I really probably should have put that in the in the abstract. Read TempDB. Right, moving to data warehousing. So is there anyone using fast-track data warehouses here? Ooh, okay. We may have conversations after this then. So they're almost an appliance. So they have a very specific setup and a very specific use. So you have a large volume of data, generally in a star schema, and you want to optimize that data for sequential throughput. So if you do something like process a cube at night or whatever massive reports, and you want to scan entire fact tables, then fast track is really, really good at that kind of stuff. There's a couple of caveats, and one of them is that you can't really have shared storage. Because you need that sequential throughput, you really need to have a dedicated SAN or some sort of dedicated carve-off for storage to make sure that none of its throughput gets interrupted if you want to get the real benefits from it. So, like I said, there's I think 2 or 3 people put their hands up there. The reason I'm covering Fast Track today is not because I think everybody should go out and try it or anything like that, although if you get the opportunity, please do. But there's a lot of stuff that you can steal from it, even if you're running on a standard SAN or if you're running on shared storage. I think a lot of people are. You know, you may have large data warehouses, but at the same time, there's probably a whole bunch of VMs on there as well. You just have a giant SAN that everybody gets a slice of, and you know, the restrictions are handled elsewhere. We'll take a look at this first. So the principle is that if you need to process data at, say, 400 megabytes per second, you'll have 2 CPUs, each of which can process 200 megabytes per second. You have 2 partitions that CPU is going to handle scanning. You've got some HBA in between that can serve at least that amount of data back. A controller with the same, that can at least serve 400 megabytes per second back. And then you'll have 2 files and 2 different sets of spindles that can serve 200 megabytes per second each. So it's very simple that if you need to double your throughput, well, you just add 2 of everything. If you need to do it again, add it again. And it does, scales linearly. So that's the beauty of it, that if you've got your own storage, you've got your dedicated hardware, you know exactly how much you want to process, how much you need to process, what time you need to process it in. It's just basic maths. Go out and buy this amount of hardware, lay out your file and file group layout in such a way that it sits on these spindles, and it all just fires up at once, pulls all the data back in, and that's it, job done. Now, the reality is, I think for a lot of people that, well, okay, I'll cover the pros and cons first. So the pros are that it's easy to figure out your needs. You have a number, you have a magic number of how big your data set is, and you have a magic number of how quickly you need to serve that data set up. And you carve that out into components. It is as simple as that. So for the DBA, it's simple, it's scalable, and it is fast. Like, it is very, very fast. If you want to crunch a lot of data very quickly, that's a very, very good way to go. And there's a lot of in-depth guidance available from Microsoft. So this is still, hasn't had a massive adoption rate, probably because of the not specialist hardware, but dedicated hardware it needs. It becomes almost like an appliance. So if you do opt to go for it, Microsoft will hold your hand every step of the way. And there's a lot of great white papers and stuff like that out there as well. The cons, so it's not recommended for pinpoint queries. And what I mean by pinpoint queries is that if you need to query the data directly, and we go back here, so let's take, for example, you've got one customer or something that you want to look up on. If you have a big report, but that customer's data is stuck on those spindles, well, then you're capped immediately. So it's a lot quicker for sequential stuff, but if you aren't getting the entire range and you're just stuck on these, well, then shared storage is actually a little bit quicker because you can use all the spindles, and while it's not pure sequential I/O, you get more I/Os, and so it's not really great for pinpoint queries. It is only really, I suppose, for processing. I have entire there, but large data sets is really what I should have there. And you kind of need a very understanding infrastructure team, because while it's easy for us to go and say, oh, I need this much throughput, so I need this many CPUs and this many disks, you're not going to be the ones going off and setting it up. And there's a tome about that thick on how to set up your hardware for fast track. And I don't know many very understanding infrastructure teams, so it's definitely, I had to put it in the cons, because I mentioned it to an infrastructure team once and I was asked to leave. So, so pattern 3, data warehouse on a SAN. And this is really the meat of the presentation here, is that, so we've got some similarities. We've got a large volume of data, generally in a star or a snowflake schema or something like that. But here are the differences. You can't optimize for sequential throughput because you're going to be on a shared SAN. So if someone's done a consolidation effort, and even though you might have a chunky VM or maybe a physical box plugged into an existing SAN, chances are you're going to have to share that with someone. So you're not going to get that sequential throughput. And it's usually, like I said, it's a mixed workload. So it's not just the data warehouse running on there. So you have to plan as such. So we have a new goal. And this is something that you'll look for as well in Fast Track, but you have to pay particular attention to it when you're sharing. So we need read-ahead. So read-ahead is key. So if you're on Enterprise Edition, which I think a lot of data warehouses are, it's capable of issuing a request for 512K of data pages on a single read-ahead request. And if you're on Standard, unfortunately, you're stuck at 64K. But it can issue several of these. Now, my testing was done on 2008 or 2, and I think since, in 2012, this can actually go up to 8 megs, but I haven't proven that yet. But just have a look at that if you're doing any testing yourself. But previously, you could go up to 4 megabytes at a time. So you can pull back 4 megabyte chunks at a time if you've got that all laid out sequentially. So, how close are you, is the question. So is anyone looking after a big data warehouse? And you do a full table scan, and you're like, yeah, that's going as quick as it can. Well, I don't know if anyone can see that, but run something like an aggregate on your massive fact table and force it to use a table scan. And the reason I say an aggregate over, say, BCP or an SSIS package or something like that is that if you have to put the data down on disk somewhere, then that becomes a bottleneck in itself. And you just want to test what your reads are doing. So something that returns a single value, doesn't have much CPU overhead or anything like that. And then you're watching this counter, and hopefully everybody can see that, but if you can't, it's average disk bytes per transfer. And this is the value you want to be watching. So my test here was doing 320, which isn't too bad. But if that's maxed, if you've got super 100% performance, that'll be 512K. All right? So that's the way to test it and baseline and see where you are. Well, because of that, and leading into this, fragmentation is the biggest problem you have. So read-ahead size will be reduced if the pages being requested aren't in order, because it will request them, but they have to be in logical order. Otherwise, it breaks up that I/O, and it has to go off and start again, and more I/Os have to be requested. So, as anyone who's a DBA does, you do index maintenance, you rebuild it, and SQL is awesome. It'll do this parallelizing, it'll split it all out. So what's the catch? Why am I moaning about it at all? Well, if you do a parallel rebuild of an index, the way it allocates the files, it grabs its extents to put the new index down. It doesn't do them in sequence. So you might have, say, take first names. First thread will grab A's. Second thread will grab a new page for B. Third thread will grab a new page for C. Fourth for D. And then back to A. So while they're all logically in order, within the file itself, they're not. So you've got A, B, C, D, A, B, C, D. So it's better than having nothing. But if read-ahead is your ultimate goal, single thread rebuilds on your indexes. I see panic. That's okay. You can rebuild at a partition level either. So you can rebuild partitions, single-threaded. Now, I'm going to put numbers on this when we get into the case study. So I did test this scenario, and it did give an increase, but when you start weighing up, right, do I really want to write something complex to do single-threaded rebuilds versus just let it do its own thing? I'll let you decide if the numbers actually make it worthwhile. Right, the next pattern I want to look at, again, data warehouse, quite simple. You have your little, I don't know if you can see my star scheme, it's very fancy there, in a primary file group, and this is actually quite a common way to find data warehouses, because it's been assigned a 2 terabyte drive, and the MDF is only 1 terabyte, so what's the problem? Well, I'll show you. But this is the most common split outside of the primary file group. So you'd have something like you have your primary, which are system tables in it. You've got a file group and some files for your dimensions. You may have a volatile staging area. And then you'll have your facts table, or your multiple facts tables in a file group on their own. Again, a step further, if you have a particularly large fact table, well then maybe you'll put that out on its own as well for maintenance, or maybe you want to do partition swapping or whatever it may be. And this, if you want to go really whole hog, and you'll see why this might be a maintenance nightmare, but this is optimal performance-wise. For each partition in your large fact table, give it its own file group or its own file. Now, management overhead, as you can see, like if you're talking about a partition based on month over a 6-year period, no, well, that even scared me. Would you bother doing it? Possibly not, but you could do a hybrid approach. So if your hot partitions can get their own file group and then start merging into older ones, but that's a management thing, so we'll get it back to that in a minute. But again, why I'm talking about all this kind of stuff, if you're a BI guy, and you do any sort of analysis services stuff, you're processing cubes at night. Now this is more probably applicable to the fast track scenario, but again, each of these partitions can be processed by CPU. If you have to do a partition scan, CPU can do them all. So while they're single-threaded operations on their own, when you combine them together, you've got parallel single-threaded operations, which is great. That's exactly what we're looking for. So with analysis services, well, how does it pull in data? If you ever watch an analysis services load, you've got this option. Process it in parallel and let the server decide how many. And when you fire it up, this happens in the background. And the specifics of that are not important, so don't worry that it's blurry. But it'll process all your dimensions, again, single-threaded, but in parallel. It'll launch a whole bunch of them at the same time. Same with the fact table. If it's got partitions or it's got partition ranges, it fires them all up side by side. We go back to this. If you've got its own partition, well, each analysis services partition is hitting one of your SQL Server table partitions, which is scanning that file. So you're maxing your CPUs, you're maxing your throughput just by going to your file group layout. So you can really, really, really increase your analysis services processing time as well. Again, all right, we do have go faster buttons. The reason I'm talking about this now, and then I want to get into the case study to actually give you some numbers and all this stuff that I'm talking about, but we did use some of these go faster buttons in the testing, so that's why I want to touch on them now. But if you have a read heavy workload and you're using Enterprise Edition, compression. Turn it on. Don't worry about it. For every I/O, like say you get a factor of 4 or even 2, you get a 2x compression. For every I/O you issue, you're now pulling in 2 data pages rather than 1. So literally, it will do double the work in half the time. And it literally does scale like that. So if you can compress it down size-wise by a factor of 4, then for each I/O you issue, each page you pull off, you're getting 4 times the data you would if it was uncompressed. So that's absolutely one to go and play with. The reason I say read heavy is that if it's a write heavy workload, there is an overhead on CPU every time a page has to be compressed. So you have to keep an eye on that. But if you've got even like an 80% read workload, look at compression, evaluate it. Apart from the disk savings, the space savings, you do really, really get a performance boost. If you're storing multiple tables in a file group, use the -e trace flag. This is for data warehouses. And what it does is, every time a new allocation is requested, so a table grows or a new row gets inserted, there's a page split, it'll ask for an extent. So 64K page, let's just store 8 pages on it, and it'll do that per file. If you turn this on, it will grab 64 extents, so 4 megabytes per object per file, rather than the standard 1. And if you think back to what we were talking about earlier, the max read-ahead that SQL can issue is 4 megabytes. So now you're starting to really line it up so that when it goes to pull the data, it has optimal conditions to pull back your 4 megabytes, get the most value for each of your requests. Because if they're laid out in the file in 4 megabyte chunks and you're doing a scan, well then they'll be fed back to you in 4 megabyte chunks. So again, really, really recommend evaluating that one if you manage data warehouses. A very standard one, but if you're using multiple files in a file group, tracefag 1117. This ensures that, so again, back to our proportional fill, they have to be equally full and equally sized. If you have a runaway query that blows up one of the files, for whatever reason, this will make sure that all files in the file group grow, so you never lose that round-robin algorithm. It takes care of the growth and everything for you. So you lose a little bit of extra space on each file growth because they all grow at the same time, but it makes sure that your performance hit doesn't happen. And in general, if it's a dedicated SQL server, and the reason I say dedicated is, well, I'll get to it at the end, but 834. So it requires locked pages in memory enabled, but I think most SQL Server standard builds kind of have that at the moment. And if they don't, it's very easy to apply. What it does is it enables large page allocations for the buffer pool. And what this means is, again, if you're thinking about a large fact table scan, 100, 200, 300 gig table scan, it has to look aside to the buffer pool, check is the page there, check does it have the memory, does it go to disk, etc., etc. If they're allocated in larger chunks, it has to do a lot less of those. And also it has to do a lot less, or issue a lot fewer requests to Windows to get memory in to let the buffer pool grow and such. The reason I say dedicated SQL servers, though, is this one. It can cause problems if memory is fragmented by other apps. And by problems, I mean shut down and cry. So, problems, right? But if it's a dedicated SQL box, you're fine. It just needs to be able to grab at least 2 megabytes of memory contiguously from Windows. And if SQL's the only thing running on there, yeah, you're fine. But again, that will, if you're doing massive throughput, that will make a big difference. Right, finally, let's put some numbers on these things. So kind of half pretend I know what I'm talking about. So as a case study, we had a fact table in a data warehouse. It was a 3 terabyte data warehouse. And the table scan was topping out at 300 megabytes a second. And this is on an IBM XIV, which is supposed to be capable of 1.7 gigabytes, moderately sequential. Couldn't obviously add indexes or change the query because it's a table scan. There was no point. The table partitioning was in place, but all of the tables were in a single file group. So they were all in that primary file group layout. And we had to get creative on enhancing throughput because that's just completely unacceptable for a large data warehouse. So I brought it back to the lab. And these are the test conditions. They're not super important, but just to give you an idea what I was working with. 16 core server with hyper-threading on, 32, 128 gigs of RAM. SQL I/O fully sequential on the storage and fully saturated would give back 2.2 gigabytes per second. Now, I wasn't expecting to get that because if I'm just running a single table scan, it's not going to get to that saturation point, but I still wanted to know where we were. And 32 range scans, which scanned a partition boundary, were started up to simulate the workload. Page compression was on, and that 834 trace flag was on, and we had max stops on the server set to 1 to make sure that it didn't go parallel on its own. Yeah?
Page or row compression?
Page. Yeah, page compression. Actually, that's a good point. If it's a data warehouse and you're read-heavy, page compression. Don't even bother with row. Row in an OLTP, if you can get away with it. But yes, page compression. And yeah, sorry, like I said, so the max stop was set to 1 because I wanted to control how parallel it went as opposed to SQL deciding, yeah, I can split this out into a parallel query. So the 32 were fired up. And this is the baseline. So in our lab, we're getting 575 megabytes per second, which is still better than the customer's one, but still not great. And this is when I'm talking about the rebuilding single-threaded, I actually got a 40 megabytes per second increase by not letting the index rebuild go parallel. So that's why it's kind of almost a recommendation. It's borderline because 40 megabytes per second versus having the custom write a parallel partition rebuild. Maybe not, but if you really, really want to push it, it actually does make a difference. The next test, get that fact table out of the primary file group and get it out into a file group on its own. And this was on the same storage, same partition even. It was just all on an F drive. Same folders, everything. Like, so it wasn't brand new storage, dedicated, anything like that. And by moving it out onto its own, we got a 60% increase in throughput. So it went up to 942 megabytes per second just by getting that fact table out on its own. And then, well, I was having a slow day, so I moved it out into multiple file groups, so one per partition, and we doubled the throughput. So 1150 we hit, all right? So literally double the throughput just by same data, same indexes, same queries, just moving it out into a different file group. And coming from a DBA world, I loved this. No code changes, no regression testing, no talking to developers. but for me, like, this is completely in my control. You know, you can add files and file groups and no one needs to know. You got a little bit of an outage or whatever, downtime while you're shuffling the data back and forth. But, you know, a 2x improvement without having to make any code changes or ask for any QA or regression testing, hells yeah, works for me. So how did this come about? So this I/O request size that I was talking about earlier, you can see on the baseline, we were only maxing out at 181 kilobytes. And we know that the max is 512, so we were way off. What I found interesting was that when I did the single-threaded rebuild, even though the request size was the same, still got a throughput increase just because they had all been laid out in the file in order. So again, that's right, how much time have you got? Might not be worth it for 40 megabytes a second, but I think it's worth testing. Almost hit 512, and I really wanted to lie for the purposes of the presentation, but no, 511 was what I peaked at on the on moving it out into its own, or the fact table out into one file group. And then when the multiple file groups, the request size came down a bit, but because we had so many parallel scans going on the partitions at the time, it more than made up for the 7K per read that I lost. So just some other metrics. The baseline, so the time it took 70 seconds from the baseline. Rebuilding single-threaded, knocked 2 seconds off it. Again, at that scale, was it worth taking the time to do a single-threaded rebuild? No, was the honest answer. But your mileage may vary, and you may find it worthwhile. So when we got the 60% increase on throughput, we got 14 seconds off the table scan time. And this is the one that kind of confused me a little bit, because we doubled the throughput, but didn't half the time. And it comes back to some links I have at the end, but basically, if you think about it, I was partitioned by date. So February is never going to have as much transaction detail as March. So it was double the throughput, but it was finishing on some partitions earlier than on others. So it'll finish the February scan before it'll finish the March scan. So your overall time didn't cut in half. You'd have to do something like hash partitioning or some sort of complex partitioning to make sure that you have even distribution across everything, which I really didn't have the time, the patience, or know how to do. So how do you make the changes? Right, now that you've all decided this is a great idea, and you're going to go back to your office and try this, and promise you won't get fired, right? It's actually pretty easy to do. For non-partition tables, you just drop your clustered index and recreate it on the new file group. So it's a little blurry there, but if you just script it out as a drop and create, this is the bit you need to change. So whatever you've named your file group, just create it on that. If it's a partition table, alter your partition scheme to point to your new file groups, depending on where you want the splits to go. And for heaps, now, apparently, again, I may be a little behind the times on this, but apparently you can do an alter table rebuild if it's a heap, and it'll put it onto the new file group. Alternatively, just create a clustered index on something unique. It doesn't matter what, because you're going to drop it. As soon as it's created, you drop it, and the data stays on your new file group. Sorry, do you have a question over there? Yeah.
Well, so you don't really need to drop the index, because you could do drop existing on.
I hadn't had any success with it. So doing a rebuild, or sorry, you're absolutely right. You could change the syntax to drop existing on. Yes.
You don't really need to drop index, which means that all your non-clustered indexes would have to be rebuilt as well.
Yes, that happens regardless, unfortunately.
Should be able to do alter index rebuild, but I don't see the syntax.
I couldn't to move file group. I had to drop and recreate. I thought alter would work myself, but I ended up having to drop and recreate it to move it onto the new file group. But you're absolutely right, you could just change that drop existing to on, and it'll do the same job. I just scripted it out.
You might, I'm not sure.
Yeah. Please do correct me if you find out, please do, because I'd like to find easier ways to do this kind of stuff as well. But yeah, for a heap, like I said, just create a clustered index on something, doesn't matter what, because you're going to drop it again at the end. But I do believe in 2012, I don't know if it came out as a service pack release or what, but you can do an alter table rebuild onto a new file group. I haven't tested that yet, so for the moment, all I do is create a clustered index on the new file group, drop it. It doesn't move the data back. Right, so summary. Your file and file group considerations can actually yield huge gains and system-wide, so you're not just fixing one query. You know, it's not like an index or you're tuning a query, you're getting out of TempDB. If you can increase the volume of I/O that it can handle, well then you're performance tuning every query that touches the box. So it's definitely worth investigating, and know your workload and optimize for it. So it kind of ties back in with if you have a hybrid workload, have a hybrid architecture. So I've covered 3 patterns today. That's not to say they're the only 3 patterns that you'll ever come across. I mean, it's super common to see an OLTP with a data warehouse kind of in an archive table underneath it. If you've got something like that where you have a hot partition, you need to service that throughput, treat it like an OLTP, add in some extra files. Then when you move it into your archive data, then have it out in a big fact table file group on its own. Whatever it is, it doesn't matter. Just, if you know your workload, optimize for it. There's no kind of right or wrong way to do it. You don't have to have one static model of the 3 that I've covered today. And don't neglect your SQL settings. So those trace flags really make a huge difference. Page compression makes a huge difference. There's a lot of things you can do without having to alter the code. That's really what I kind of want to get across today, is that you don't need to make code changes. Well, yeah, sometimes you do. Sometimes you just have to add an index, and that's, yeah, fine. But trace flags can make a huge difference to your workload. Like I said, a table scan is a perfect example of when you can't apply an index to make things better. So, well, come at it at a different avenue. Try trace flags, give it a file group, give it new storage. And code changes and indexes aren't the only way to save the day. Like they're very quick, and they do help, and sometimes they are the cure. But you can have an estate-wide or an instance-wide, database-wide improvements by just looking at the underlying architecture. Some useful links, and this is going to be available for download as far as I know. Some of these are really, really excellent. I will give them a go. The top one is the Paul Randall multi-file and file group testing on Fusion.io. So that'll be the OLTP testing I did. It's a slightly deeper blog on exactly what he did, his test harness, and some of his results. And he went, like I stopped at 8 files. I think he went to 32 or something like that. It's a good kind of 10, 15-minute lunchtime read. The fast track configuration guide. Even if you're not using a fast track data warehouse, I would highly recommend having a look at that. There's a lot of hints and tips in there, which is the likes of that -e trace flag, and there's a couple of other links onto how to data load faster and stuff like that. You don't have to read the whole thing. There's a section on SQL Server configuration. It'll take you about 5-10 minutes to go through it, and I'd highly, highly recommend having a look at that. The next 2, resolving latch contention and maximizing table scan speed. These come back to that hash partitioning and getting the even distribution across your files, your file groups, and your partitions in the data warehouse or OLTP, whichever. Heavy reading, very heavy reading. However, if you're really going to go to the next level with it, it's definitely worth looking into. To be honest, there are probably about 999 things I would do in front of that to have to avoid it, because it is super difficult. But it's definite if you want to take it that next step further and really, really push your max out your performance. Those 2 are very, very good. My colleague Bob Duffy wrote a specifying storage requirements guide for DBAs, or for non-storage professionals. The reason I linked to it is that there is a good guide on how to use SQL.io, how to parse the output, and how to make it presentable, and then go and talk to your storage dudes about, right, this is what I need, this is what you told me it can do, which is a very common argument. So yeah, of course you can do 20,000 IOs, and then you find out you're doing 5,000. That's the kind of stuff that that blog is very, very good for, and you can kind of get it into a very presentable fashion and hand it over to them. Fragmentation in data warehouses. So a guy called James Rowland Jones, he's a UK speaker. At SQL Bits, he did a session on its fragmentation in data warehouses. Now, it's geared a little bit towards fast track, but as I showed today, the concepts apply across the board. So it'll go into why fragmentation causes problems. It's about 45 minutes long. If you really want to tackle something like this, I'd highly recommend it. It's a lunchtime session. It's a very good one. And the last one is not performance related, but I'm trying to give you reasons to go and do some of this stuff and then send me emails about, what terrible advice that guy gave us at SQL Rally. But partial database availability and piecemeal restores. So Kimberly Tripp did some MCM readiness videos on partitioning and high availability and how to do, very quick restores and file group based backups and all that kind of stuff. It's file group maintenance and manageability. I highly, highly recommend you go have a look at that. And if you're going to put some thought, time and effort into actually designing a file group layout, well then you may as well get the most out of it. Approach it from both avenues, performance and manageability, and make your lives easier. So that's all I've got. Are there any questions or anything? I don't know if that's a good or a bad thing. Either it's useless or I explained it really well. I'll believe I explained it really well and no one needs to ask me anything. Well, look, guys, thank you very much. I really appreciate you taking your time out to come to the session. And anything after the fact or any questions, please drop me a line. I'll stick it back on the About Me just in case anybody wants to send me hate mail. Any mail is good mail, I don't care. And sorry. There we go. Yeah, please, any questions, comments, anything at all, any war stories, horror stories, love to hear them. So please do get in touch. All right? Thank you very much. Appreciate it.